Now, how do I quantitatively, how do I mathematically write this? Just like we did last time. So this is going to be a loop rule. It will be EMF of the battery equals delta VR plus delta VL, or IR plus L DI over DT for switch at position A. So this is identical to the RC case, and I will not do it. With the boundary conditions now at T equals 0, I equals 0, and at T equals infinity, I goes to E over R. So I will leave it up to you guys to derive, but my final result for homework to derive that, E over R, 1 minus E minus T over tau L. Where tau L is defined as L over R, and it is called the inductive time constant. I think I made this color last time, so I'm going to leave it at that. And this tells me how rapidly the current approaches steady value. And if you wanted to check what the units of TL were, they are actually Henry per ohm, where Henry was volt second over amperes divided by volt over amperes. So amperes will go away, volts will go away. What am I left with? Drum roll. Seconds. Okay, and we did these graphs last time. For increasing and decreasing, we're going to do exactly the same graphs again, and they will look like VR. I'll do VR first. Okay, this is actually, let me do a dotted line here. Let's do that. And delta VR and delta VL. So this, if this is 10, this will look like this. And this will look like that. Where delta VR mathematically is given by IR or E1 minus E minus T over tau L. And this is given as delta VL L di over dt or E to the minus T over tau L. There's literally like one step in between all of this. But remember, for this case, this will always hold true, that the potential drop across VR and the potential drop across VL, the sum of them will never be greater than the EMF that the battery provides. Okay, last thing. What happens now? All of this happened when the switch was at point A. Correct? Now, what happens if I take this switch? Okay. And instead, join it here. What will happen? So for part B, next, move the switch to B. So basically what you've done is you've done this. You've taken the battery out of the system. So your loop equation will become di over dt. Or once you solve it, I as a function of time will just be I0 e to the minus t over tau L, where I0 is the current at the time when switch is changed to position B. Now take that as time t equals 0. So your graphs will look like this. So let me draw the same graphs again. This is delta VL. And this is delta VR. Oh, and I forgot to mention, these conditions are for when R is taken to be 2 kilo ohms, L is taken to be 4 henries, E is to be taken as 10 volts, and tau L, you can calculate it to be 2 milliseconds. Here, remember, delta VR plus delta VL must equal 0. Here it used to be that it was equal to VR. Here it will be equal to 0.